Hello, everyone. I'm Anson. I work on Azure Kubernetes Service. I love to help users to achieve large-scale, high performance, and hopefully at a reasonable cost. By now, you probably have heard a lot about optimizing Ray itself. And today in this talk, I'm going to focus on control plane and how to build a system around Ray to validate the scalability and tune performance of GPU scheduling and KubeRay orchestration, and without robbing the bank. So here's the agenda. I will first provide some context around the why and the how, then walk through some concrete examples, and finally discuss area for future work. So how many GPU nodes and Ray pods can fit into a Kubernetes cluster? How would new features like dynamic resource allocation affect performance at scale? I got this type of question a lot from Ray and Kubernetes user. For example, recently at Microsoft AI, we have many researchers constantly run Ray-based training job on GPU nodes from small to medium scale for experimentation purpose. And once in a while, the researchers put together latest data and code for a large training job to train production models. This is the time when everyone gets nervous. So we watch the system and job very closely, like watching a rocket launch. And as Murphy's law predicts, things can go wrong, will go wrong. When the big day arrives, researchers launch the large-scale job, engineers scramble to debug and fix issues. I've been in that situation, troubleshooting job startup failure or delay, a lot of times due to pod not created or stuck in pending state, sometimes DNS query error, sometimes image pool timeouts, so on and so forth. Meanwhile, the valuable GPU resources sits idle, just due to job run fail and delay, and now engineer has a problem to solve. In theory, one solution could be use synthetic workload that mimic real-world usage pattern, and we run automated tests to evaluate the performance at the desired scale. Why automation? It is essential because it provides enough data points for us to get a statistically meaningful test results. Only with enough data points, then engineers have confidence to roll out the new changes. It also enables engineers to do early detection of a performance regression. So it sounds like a good plan. This is the reaction you are likely to get when you request the budget approval of 10,000 GPU nodes just for testing. And even if you get approval, the on-demand or spot capacity from any cloud provider will typically fall short due to the GPU scarcity. What about reserved capacity? So that makes the cost of the running continuous large-scale benchmark too expensive to be practical. Now what? So here's the simple idea. While the researchers run experiment on real GPU, engineer can use a virtual GPU to exercise control plane. So Kwok is a Kubernetes upstream project that can simulate GPU and CPU node lifecycle as well as Ray pod lifecycle. It can mimic real-world usage pattern and generate a realistic load on any real control plane, whether it's cloud-managed, self-managed, or even locally in a CI/CD environment. Now we have a solution. Here's the example setup look like. So class loader tool is used to submit RayJob and RayCluster to the Kubernetes control plane. KubeRay operator reconcile custom resource into pods, while the pods are assigned by the Kubernetes control plane to virtual GPU nodes. The node and the pod lifecycle are simulated by a Kwok controller running on real CPU node. Finally, the last piece is Prometheus and Grafana are used to collect and visualize metrics from the control plane for performance measurement and analysis. So I hope this doesn't feel like a sales pitch, but cloud-managed control plane are highly cost-effective. So running a managed control plane only costs 10 cents per hour. And with only 3 real CPU nodes running the KubeRay operator, Kwok controller, and Promise and Grafana, it is now feasible to run large-scale benchmark for less than $10 per hour. Here's one example test results showing how topology-aware scheduling enabled by dynamic resource allocation could lead to lower maximum job throughput measured by numbers of pods per second. What's more concerning is as the cluster size increase, this throughput gap actually becomes even bigger. So why is that? Analyzing the metrics reveals there's a substantial backlog of resource claim for the Kubernetes controller manager to process before Ray pod can be even scheduled and executed. So resource claim is needed for every pod to allow the workloads to specify the exact type and the amount of GPU resource they require. So that's the overhead of dynamic resource allocation. Reading the Kubernetes source code, I noticed the default value for resource claim controller worker are initially set to very low, only 10. And later on, it's increased to 50 by the community. However, even 50 workers still are not sufficient for large-scale workloads at a 10K scale. So, but increasing the number will introduce trade-off. With more workers, there's more APS overload, and also the CPU and memory consumption. So to address this, I opened a pull request to make the value configurable. And currently, it's a pending approval from the DRA SIG. To scale KubeRay orchestration, there are also several parameters to tune. Luckily, the latest version of KubeRay Helm chart exposes new options for large deployments. This is including reconcile concurrency, Kube client rate limits, and naturally, the CPU and memory limits need to be increased to avoid CPU throttling and OM kill as numbers of custom resources need to be cached. The Kubernetes control plane also offers many knobs to tune. Again, my intention here is not to show which knobs to tune with what value, but mainly the idea using automated benchmark and continuous monitoring to validate the settings as it changes in a very rapid environment. Especially nowadays, performance bugs due to human error or AI hallucination can slip through code review and lead to production issue at any time. Last but not least, I think it's equally important for researchers and engineers to agree on performance and scalability SLA. For example, what level of job startup latency at what scale is acceptable for researcher and achievable for engineers. So the scenario and the measurement covered so far by no means is comprehensive. Scaling up by a factor of by 10 will inevitably expose more new bottlenecks and require new optimizations. It is also very common to see runtime failure during large-scale job training in GPU cluster. For example, node can be cordoned and drained as a GPU device burn or NVLink InfiniBand flap, and this is going to cause a Ray pod to fail over and churn. And Kwok is in a good position here to push for hyperscale and also inject failures to get closer to the real-world use cases. So that's all for today, and thank you all for attending this talk. Here are some links to examples to show you how Kwok integrates with Ray and DRA, and feel free to take a look, and hopefully this will be useful for you. Thank you all.